notes. The one thing I maybe forgot to mention is when you go to actually hand it in, I'm going to ask, it's the same thing, you'll submit a PDF of your homework. Did that work okay with homework 1? Everybody navigate the Canvas upload thing fine? Yeah. But for this MATLAB problem, you can just copy all that code, paste it into your Word document. Also, those images those graphs I created, you can also, and there's an upper toolbar on it, you can just copy the image and you can paste that into your same Word document too. Okay? You don't have to send me the MATLAB code itself. Quite frankly, I don't want to open them all. And so we'll see how that goes. And we can keep getting into MATLAB, make sure that this is something that's working for everybody. Yeah. Okay. Well, let's let the game continue at least a little bit. We got some time. That's not the page. This is the page. I've been throwing around this term. Oh, by the way, a couple people have pointed out that there's at least one mistake in the answer key so far. That we'll see. I knew I should not post the answer key before I actually started grading. Because, by the way, do you know how we teachers work? We write the answer key, and then we grade the first paper. But the first paper we grade isn't actually grading the paper, it's grading the answer key. And so it's when you grade that first paper when you find all the mistakes in your answer key. And I apologize for that. There are a couple kind of sloppy errors in there, and I'll get all of those fixed for you. Anyways. Okay.
I'll ignore the errors in yours if you ignore the
There
errors
you
in
go.
mine.
There you go. I'd say.
Call the draw.
Okay. So you've heard me use the expression independence quite a bit so far this quarter, and I've been kind of appealing to a general understanding of what the word means in general. Let's apply an actual mathematical meaning to it now. And indeed, it is as it says. Independence, I think, I don't know what section we're in now. Is this 5.4? Is this 5.5? Not sure. No, I mean 1.4 or 1.5.
I was about to say that.
Yeah, we're not in my other classes in chapter 5. Okay. Independence. Just verbally, events A and B are independent if the occurrence of one of them does not change the probability on the other. Otherwise, I'll say, otherwise, A and B are dependent. Okay? And so, mathematically, that sentence, events A and B are independent if the occurrence of one does not change the probability on the other. Or in other words, the probability of B given A is the same as the probability of B. Right? Mm-hmm. Namely, the occurrence of A has no effect on the probability of B. Okay? And so another thing I'd add at this point is what was that other thing I was going to add? Oh, and when you think about it, I know there's a tendency to think about the words independent and dependent as being two extremes, kind of polar opposites of each other. That's actually not the case, okay? independence is this statement right here. The probability of B is not changed by the occurrence of A. Anything shy of that is dependent. Okay? It might be a subtle dependence, it might be a gross dependency. Okay? Okay? Now, if A and B are independent, then B and A are independent. Okay? Okay? This is not about cause and effect or anything like that. So if A doesn't affect B, then B does not affect A. Okay? Okay? And or the probability of A given B is the probability of A. Or recall that the probability, in general, the probability of A and B is the probability of one of them times the probability of the other given the first, right? But if A and B are independent, right, then the probability of B given A is simply the probability of B. So the probability of A and B is the probability of A times the probability of B. Okay? Okay? These three statements, those three statements are mathematically equivalent in the sense that either they're all true or they're all false. You can't have one of them true and another one false. It simply doesn't work that way. Okay? Okay? These three statements are either all true or all false. So any one of them, any one of these could be used to validate independence. In fact, as things move on, this last line, this product rule, the probability of the intersection is the product of the probabilities, right? That is kind of the go-to, okay? Any of these can be used, right? Right? But oftentimes this last one is the easiest, and this last one is the one that extends to more than one event. Please.
Is the probability of the intersection being the product of the individual probabilities, is that true for dependence and independence, or just independence?
Just independence. Okay. Right?
Yeah, that makes sense.
Right? And so this here is there's money in that equation right there. Okay? Okay? And so for instance, let's toss a coin 2 times, right? Find the probability both land on heads. Right? Now, independence comes up either like in the specific context of the problem, like flipping coins or rolling dice. The trials are independent of each other, right? the fact that the first dice roll landed on heads doesn't influence what's going to happen with that second dice roll, does it? Right? The trials are independent, right? And so before, when we did this problem on the first day of class, we probably did this problem on the first day of class, we said that the first dice could either be a head or a tail. The second dice could either be a head or a tail, a head or a tail. There are 4 equally likely outcomes. Equally likely outcomes. Thus, the probability of head-head is 1/4. Remember back day 1, that's how we did that? Equally likely outcomes. Now, right? When we first visited this problem, right? Now, the probability of a head on the first toss and a head on the second toss, right? The result of the tosses are independent of each other. Right? The result of the trials are independent. I like saying it better that way. The trials are independent, which means the probability of the intersection is the product of the probabilities, is the probability the first coin is a head times the probability the second coin is a head, probability, which is 0.5 times 0.5, or there's the quarter we got before. You see what I mean? You see what I mean? Right? Now, this first approach, right? So now we can solve like this. Right? Now here's where there's an awful lot of power in what we just wrote there, because this first approach we did here demands that the outcomes are equally likely, right? But what if they're not? Right? Then that upper method doesn't work anymore, right? This has no condition on the equally likely part, right? And so now this second approach can be used when outcomes are not equally likely. Right? For instance, let's roll a 6-sided dice. Right? Find the probability, I guess that this is kind of the same example, that both dice land on a 6, right? Well, again, you all did homework number 1, and you all did question 1 on homework number 1, so you probably all have that little graph with your 36 outcomes on there, and there's one outcome that has double 6s on it, so you know the answer is 136 from that, right? But probably an easier method going forward is let's let AI be the ith roll lands on 6. And in this case, I is just 1 and 2. So the probability that the first lands on 6 and the second lands on 6 is, how about dice rolls? Do they follow the same as coins, that the different rolls are independent of each other? Yeah. There's no hedging our bets unless you're in Las Vegas or something like that, right? And so because of independence, that's the probability. The first is a 6 times the probability. The second is a 6, which is 1/6 squared, or there's that 136 we got before. You see what I'm saying there? Right? Right? And how do we get something like this? And so independence is achieved through, maybe 1 inherent to the experiment, such as flipping coins or rolling dice. Okay, which is why we start with examples like that, or designed into the experiment. Like we were talking about testing your circuit under multiple trials, right? You really want those trials to be independent of each other, please.
So, to see if I'm getting this concept straight, last class we had an example using a deck of cards.
Mm-hmm.
That draw a random card out of the deck of cards, and what suit is it?
Mm-hmm.
If we are removing the card from the deck of cards, the trials are dependent.
Yep.
Because the last thing you drew will affect the probability of the next thing you draw.
True.
If we replaced the card, though, the trials would be independent.
Absolutely right. Did you all hear that?
Mm-hmm.
You know, with that deck of cards, you know, if you're pulling it out of the pool and never putting it back, then those probabilities are changing with each stage. That would be dependent. If you're putting that card back in again, then those probabilities are remaining the same. You're 100% right about that.
Okay.
Yes, yes. And so please.
I guess to follow up on that, we can know if something becomes dependent if the experiment changes the original omega.
If there's something inherent in there that changes it, yeah. The other quote unquote way that we get independence, or at least virtual independence, is if you're sampling a relatively small number from a huge population, right? You know, for instance, I'm taking a random sample of 5 people and asking if they're right-handed. Well, if I remove one person from a pool of 200 million, that really is not going to change that probability in any kind of a meaningful way. Do you see what I'm saying there? And so another way you get independence is through random sampling. With a relatively small sample from a large population, right? And in fact, in true sampling theory, what you do is you put that person back in the population again. So in true sampling theory, a person could be selected for a sample twice. You know, the odds of that happening are ridiculously small, but you know, and so for instance, according to Wikipedia, approximately 90% of the population is right-handed. We randomly select 3 people, right? What's the probability they are all right-handed? Right? Now here I'm selecting from a huge overall governing population, like the population of the world or the population of the country, right? I'm not necessarily sampling from the engineering department I worked in. You know what I mean? Yeah.
But in this event, what the scenario you've described is a partition. Does that matter? Because you're either right-handed or you're not.
You're either right-handed or you're left-handed, and what that does is help you construct a tree if you wanted
Okay.
to, you know. So for instance, yeah, recognizing that is important, that because, the question might be, what's the probability 2 of the 3 are right-handed, and even if you want to include the ambidextrous people in your group, you can classify people as righty or not righty, exclusively righty or not. And so the problem now I can't even appeal to examples we did on the first day of class about coin flipping or dice rolling, I can't list out all the outcomes, okay, so to speak, with a population huge. So the probability the first is a righty and the second is a righty and the third is a righty, by independence, it's the probability the first is a righty, probability second is a righty, probability third is a righty, or 0.9 cubed. Right? Yeah.
This might be getting too philosophical.
Okay.
For a class like this. At what point can we say with certainty that an event that we don't know the exact control of is independent? Because coins and cards and dice, I agree.
Yeah.
But also just the population, there's so many factors.
There are things called hypothesis tests.
Okay.
Where you can test a claim, and that's a little bit beyond the scope of us, but if we would, the way that would work is you'd start with a tentative assumption that they're independent, and that independence would imply a certain probability, and then you observe something else. And if that you actually observe varies greatly from that initial assumption, that gives you evidence to reject that null, And so there are a lot of details in there, but yeah, that's the whole point of hypothesis testing, is to do things very much like that. And there are tests called, goodness of fit tests, test for independence, because that is the ultimate question, Somebody back in the day wanted to know, is high blood pressure and diabetes, are they correlated or are they independent of each other, right? And so how do we do that? We do some sampling and we test it against that claim, right? And so very good. Now, what else can I say? I can say I did something in that step right there that I probably should expand on just a little bit, because I talked about independence for just 2 events, and then I did an example where there were 3 things going on there all of a sudden, okay? And so we could bring up, now this really is not going to come up in the context of this class, but an expanded definition of independence, an expanded definition of independence. Okay, let B1, B2 out to somewhere, BK be a set of events, okay, and let's make it a set, okay, and let's let S be a subset of that, B1, B2 to BK, okay, then the overall set, B1, B2 to BK, is independent if for every subset S, the probability of the intersection, BI, okay, BI contained in S is equal to the product. Have you ever seen a grand product written as a pi sign like that? You know, it's the summation. Summation is for addition, as this pi sign is for a string of multiplication, right? Right? For BI contained in S, the probability of the BI, i.e. the multiplication rule. Okay. Any time in this course we say things are independent, we're going to mean this overarching definition of independence. Okay? Okay. I will also mention pairwise independence. Pairwise, independence is when the probability of BI and BJ is the probability of BI times the probability of BJ for all IJ provided I and J are not the same. Okay? Okay? And by the way, independence implies pairwise independence, doesn't work necessarily in reverse. Okay? Okay? So in other words, if I have a string of independent events, then the probability of their intersection is the product of their probabilities. Should I write that this means product of? Since I'm assuming that's a product of. Okay? Okay? Just like what I did over here, right? The probability of R1 and R2 and R3 simply becomes the probability of R1 times the probability of R2 times the probability of R3. Okay? Now, what else is of interest here? How are we doing? We're doing great. Okay. Let's see if we can do this. Here, claim. If A and B are independent, then A complement and B complement are also independent. By the way, it's also true that A and B complement are independent, and A complement and B are also independent. Okay? Let's see if we can convince ourselves of this in our last 15 minutes. We'll see how this goes, right? And so we need to show that the probability of not A and not B is equal to the probability of not A times the probability of not B. Okay? Okay. Fantastic. And not only do we need to show that in good proof form, we need to intrinsically use the fact that A and B are independent. Okay, now this isn't a proof writing class, and I'll never ask you guys to write anything like a proof or anything like that, but it's good to see you're in a stats class. Okay, so the probability, here we go. Probability of not A and not B is the probability of A or B not. Right? What rule did I use to do that?
De Morgan's.
De Morgan. That's a De Morgan step. Right? And that is 1 minus the probability of A or B. That's the simple definition of complements. Right? Right? And that is 1 minus, let's see, the probability of A plus the probability of B minus the probability of A and B. Right? That's just inclusion, exclusion. all things we've talked about. Okay, now we're assuming that A and B are independent, right? Right. By the way, in a good proper proof, I probably would have started with a first line, pick events A and B, assume they're independent.
Do we carry that complement through? Because from De Morgan to the next step under 1 minus probability of A or B.
Right there?
Yeah, because
Yeah.
then, and then to the next step.
Yep.
We have gotten
Now
rid of
we've used the complement rule, so we've
Oh,
undone that.
you're right.
Right there, right? And so everything right here is spectacular, okay? Now I can use the fact that we've assumed for these generic events A and B that are independent, we can use that right here, right? And so that is 1 minus, and I'll keep that parenthesis there for a second. It's the probability of B minus the probability of A times the probability of B. I love that, okay? A and B are independent. Tidy this up a little bit. 1 minus the probability of A minus the probability of B plus the probability of A times the probability of B. And you stare at that thing. You stare at that thing, wondering what the point is, right? That thing factors. That thing factors, okay? And it factors to 1 minus the probability of A times 1 minus the probability of B. Right? Foil that out, you'll convince yourself, right? There's my 1, there's my minus the probability of A, there's my minus the probability of B, there's my plus the probability of A times the probability of B. And you see what we've got automatically? This side here is the probability of A complement. This term right here is the probability of B complement, and we are done. Right? So indeed, if A and B are independent of each other, then so are their complements. Right? And any other, and by the way, if you wanted to, if you were feeling like you wanted to beat yourself up a little bit and you wanted to prove that something like A and B complement are independent, this is a structure that can get you through that argument. Right? If you ever take something like math stats, then you'll do things like this in your homework. Okay, good. And so, how are we doing here? That didn't take too long. Okay. Yeah, and so, let's say, this is the season, isn't it? Let's assume, I don't know. I'm making this number up because I really don't know. Example, let's assume that 60% of tax filers, or how about 30%? I'm going to change my question. 30% of tax filers request an extension. Okay. We're going to pick randomly. We're going to pick 4 random tax filers. Okay. That's A. Find the probability that all 4 request an extension. Well, we'll keep asking some questions here, okay? And so let's let first off, so the first one would be like the probability of T1, and the second one does, and the third one does, and the fourth one, they all file for an extension, right? Again, a small sample from a large population, okay? And so you know, don't forget we remove one person who requested an extension from the pool of millions who extend. It doesn't change that probability in a meaningful way, right? Do you see that looks like probability of T1 times the probability of T2 times the probability of T3 times the probability of T4, or 0.3 to the fourth? How does that look? Does that look okay? 3 to the fourth? And similarly, find the probability that none of the four request an extension.
The complement?
Is it the complement? Is it the complement? How about that first one? Let's see, the first tax filer didn't request one. The second one didn't request one. The third one didn't request one. The fourth one didn't request one. Right? Right? See, I'm not sure if it would be complements, because don't forget, if you were, not that I'm saying you should do it, but if you were going to draw out that tree, right? First person either is a tax filer or not. Extends to the next one and the next one, right? On that big tree, isn't this only one branch? Right?
Yes, because it's
And
not
is
at
this,
least
and is
one
this
of-
all the remaining branches, or is this something different?
That's something different.
Yeah,
It's the very bottom tree.
See
We're
what
done.
I'm saying there? So all and none are not complements of each other, right? Right? Instead, it's the probability the first one doesn't times the probability the second one doesn't, so forth and so on. Probability the third one doesn't. Probability the fourth one doesn't. And to write that out in notation we're about to see in a minute, that's 1 minus the probability, or 1 minus 0.3 to the 4, or 0.7 to the 4, whatever that would be. Right? Right? Ah. See, but find the probability one or more file for an ask for an extension. Request an extension. Right, right. Now, what do you think about this one? So either one person, one of the four, or two of the four, or three of the four, or all four of the four even, right?
So we find those individual probabilities and add them?
Do we? Are they disjoint?
No.
No, they're not. Good observation. Mathematically, really what we're asking is T1 or T2 or T3 or T4, right?
So we have to add and then subtract the crossover.
You could use inclusion, exclusion, but there are 4 events there. Inclusion, exclusion sounds to me to be pretty nasty, doesn't it? Right? You're absolutely right. It could happen, right? Right? But I would tell you, by the way, through talking about conditional probabilities last week, and we had a multiplication rule for intersections. Here we have independence, and again another multiplication rule for intersections. Intersections are really kind of your friend, aren't they? Because they're describing one thing that's happening on that tree instead of a whole multitude of things happening, right? Right? And here's a place where I would consider, inclusion, exclusion is an option, right? It's also 1 minus the probability that that's not the case, isn't it?
Because the only scenario in which one of them, at least one of them, doesn't, is the complement of it's none of them.
Ah.
The only scenario in which none of in which there is not at least one extension is that none of them have an
And,
extension.
how can we express that in that last line?
De Morgan.
De Morgan. This is where De Morgan rears its head, right? You know? And so that's 1 minus the probability of not T1 and not T2 and not T3 and not T4. Now you can use independence, right? Which is 1 minus, and you know here now use independence. In fact, I think we've got the answer to that, 0.7 to the 4th, right? Right? You see what I'm saying there? How's that feel for everyone? Oh, our time is about out. We could keep going with a whole bunch more questions about this. Seems like next class, at least really the first half of class, we'll still be talking about independence. Okay? Yeah.
So, if I'm observing this correctly, all and none are not complements.
Nope.
But none and at least one.
Exactly
are
right.
Okay.
Exactly right. You know? And that bears out when you think about that tree, because there's only one branch that's gonna be all of them, and then all of the others will have at least one missing. Yeah, yeah. All right, we'll keep this up come next class.
Sweet.